Welcome back to this next video in which we are discussing the product of two subgroups. Okay, so what we're going to move on to in this video is discussing criteria for the product of two subgroups to actually be a subgroup itself. Okay, so here we go. We will call this next theorem Theorem 2, and this is going to be a really important theorem. Now, in Theorem 1, we were assuming that the subgroups that we were working with were finite subgroups. In Theorem 2, we're going to go back to having fully general subgroups. Okay, so we're going to assume no such thing anymore for Theorem 2. Our subgroups H and K could be infinite subgroups, of course, if our group, capital G, was an infinite group. Okay, so we're back to pure generality. And here comes Theorem 2. So Theorem 2 is that the product of H and K, okay, capital H and capital K, the product of these two subgroups will be a subgroup itself, so will be a subgroup of G if and only if, and I'll write if and only if for short as if with double F here, so if and only if HK, the product of H and K, is exactly the same as what you'd get if you took the product of K and H. Okay, so hopefully you'll be aware of what the left-hand side here means. Hopefully you'll be aware of what it would mean for this subset to actually be a subgroup. Let's just elaborate a bit what the right-hand side here means. Okay, so this means that these two subsets of G must be exactly the same. So both of these are subsets of G. To construct H producted with K here, what you would do is, as we've defined, you take all elements of H and compose them with all elements of K. So you take all little h and all little k from these two subgroups and compose them together in this order, where you've got the element of H at the front and the element of capital K at the on the right here. Okay, so where little h is an element of capital H and little k is an element of capital K here. So that is H producted with K, the set H producted with K, but of course what we could also do is product K with H. And by definition this would be all things of the form little k composed with little h, where little k is an element of capital K and little h is an element of capital H. And this side of this statement here means that these two sets here, these two subsets of G, both of them will be subsets of G, must be exactly the same. Okay, so it's not trivial that these are exactly the same. Okay, it would be trivial if we were working in an abelian group. If we were working in an abelian group, then little h composed with little k would equal little k composed with little h, and therefore truly these two subsets will be equal to one another. However, even if you're not working in an abelian group, it might be the case that these two subsets actually end up equaling one another, even though it is not true that little h times little k would necessarily be equal to little k times little h. It just has to be true that there is some element in this subset over here which is equal to each element back here. Okay, so these two subsets must be the same if it's going to be the case that the the product H and K of K, the product of H and K here is going to be a subgroup of G. Okay, so this is Theorem 2, and this is an if and only if statement. So if this is true, it's true that the product of H and K is a subgroup of G, and of course, if this is true, it will be true that K times H is the same as H times K, so K times H will also be a subgroup of G. It will be the exact same subgroup of G, and it's only if as well, so the only way for this to be a subgroup of G is if this is true. Okay, so we'll start by proving if, and then we'll move on to the only if. Okay, and if you don't fully understand this right-hand side yet, you will understand it by the time that we finish this proof. Okay, so let's start off by proving the if. So, what we want to prove then is this arrow here. We want to prove that if this is true, i.e. if it's true that the subset of G that is the product of H and K is the same as the subset of G which you get if you product K with H, then it will be true also that the product of H and K is a subgroup of G. Okay, so we want to prove this arrow here, so if. So we're going to start with the assumption that this is true and prove that this is actually going to be a subgroup of G. Okay, so what do we need to do then? Well, we need to prove that this subset is actually going to be a subgroup. So firstly, we need to make sure that it's a non-empty subset. So why is it going to be true that the product of H and K is always going to be a non-empty subset of G? Well, the reason it's going to be non-empty is because at the very least, these two subgroups here, H and K, will have to both contain the identity element, and therefore one of the products that you're always going to have is the identity with the identity, and therefore at the very least the product of two subgroups is always going to contain the identity element, so it's going to be a non-empty subset of G. Now what we need to prove is that it's a special non-empty subset of G. It actually obeys the axioms of a group in its own right, with the restricted composition law on it from the larger group. So we need to show that it is closed under composition, that it's associative, but of course we don't need to worry about that. Throughout this playlist, we've seen a lot of examples of checking that subsets are subgroups, and we know that whenever you take any subset of a group and you restrict the composition law down to that subset, the composition law will always obey associativity whether the subset is a subgroup or not. If it wasn't the case that that restricted composition law did obeyed associativity, then it wouldn't have obeyed associativity as part of the larger composition law on the entire group. So you can always instantly conclude that associativity is fine. Then we need to check that the identity is in that subset, which we've already stated it is, but I'll write it down anyway. And then we need to check that inverses are there. Okay, so let's do this. So axiom number 1, closure. So I want to check that if I take two arbitrary elements of this subset, and I'll call my arbitrary elements little h composed with little k here, and another one, little h bar, and I'll try and make the little k a little bit smaller than that one, little k bar here. Okay, so these are my two arbitrary elements from capital H producted with capital K here, the product of capital H and capital K. So I've taken two arbitrary elements, and of course an arbitrary element is of the form an element of H composed with an element of K, which is what these two things are supposed to imply. Okay, what I want to make sure is that if I product these two together, so if I product little h times little k with little h bar times little k bar here, that the answer is still going to be in capital H times capital K here. Okay, i.e. that it's closed under multiplication. If I compose any two elements in this subset together, I want to get another element that's back in the subset. Now note, the reason I haven't bothered putting any brackets in here is because I know I'm working in this larger group, capital G, which obeys the axioms of group theory, and therefore composition is going to obey associativity, so I don't need to bother putting brackets in. Wherever you put the brackets, the answer is the same. Okay, so how am I going to prove then that this element is going to be in the product of these two subgroups here? Well, what have I got that I know is true? I know that the product of H with K is the same as the product of K with H. Okay, and somehow I have to use that piece of information to show that this is of the form an element of capital H composed with an element of capital K. So here's the trick. Look at this portion in the middle. K composed with H bar. Imagine putting brackets around that, and let's think about that. That is an element, and I'll just write it out in its own right. Little k composed with little h bar here. That is an element of capital K producted with capital H here. Okay, the reason being it's just an element of capital K composed with an element of capital H. Okay, so truly it's going to be an element in there. But I know that these two sets are identically equal to one another, so that means there must be some element in here that is equal to that element, i.e. if you work them actually out, they give the same answer. Okay, so there must be something which I'll call h prime times k prime, little h prime times little k prime here, where little h prime is an element of capital H and little k prime is an element of capital K, which is an element of capital H producted with capital K, such that when I work this out I get the exact same answer as that. Okay, and that's because these two sets are equal to one another. So this element, if it's in there, there must be some corresponding element over here, and all the elements over here are of the form an element of capital H composed with an element of capital K. Of course now it's obvious what to do. Just substitute that in here and we'll get that this is h composed with h prime, composed with little k prime, composed with little k bar. Okay, and now of course h composed with h prime is just going to equal some other element of capital H, because capital H is a subgroup, and what should I call it? I'll call it little h hat. I'm rapidly running out of alterations that I can make to the symbol little h. Okay, and I'll call k prime composed with k bar, I'll call that little k hat here. Okay, again, because capital K is a subgroup, so if I compose two elements of capital K together, I'll get another element of capital K. So this now becomes little h hat composed with little k hat, and of course that's obviously something that's in capital H productive with capital K. Okay, so truly, when you product two elements of this subset together, you are going to get another element of the subset. If this is true, we used the fact that this was true in order to prove closure there. Okay, so now on to the other axioms of a subgroup. So axiom 2, associativity, we don't need to worry about. Axiom 3, the identity element of the larger group must be in there. We know that that's going to be true because both capital H, well, that you don't need this to be true in order for that to be true, because both capital H and capital K both have the identity in. So one of the things that you will get in this product of these two subgroups is the identity composed with the identity, which of course will equal the identity. So the identity is always going to be an element of capital H productive with capital K, whether or not this is true. Okay, so whether or not this ends up being a subgroup. Okay, so that one's fine. And now inverses. Okay, so we need to prove that inverses are going to be in here. So I need to prove that for an arbitrary element, little h, little k, which is in my subset, which is the product of the subgroups capital H and capital K, I need to prove that the inverse to this element is also in there. Well, what is going to be the inverse to this? Well, one way that you could get the inverse is by composing K inverse, so K will have some inverse in G, with H inverse. Okay, so little k's inverse, I'm denoting little k inverse here, and little h inverse here. Okay, little k inverse is going to be in capital K, and little h inverse is going to be in capital H, because they're both subgroups. And this thing here, this is certainly therefore going to be in the product of K and H, because here's just an element of K composed with an element of H, and this is going to be the inverse to this element, because if I did compose them together, I'd end up with the identity. But now, of course, we use the fact that this set is equal to this set, so there must be something in this set that is equal to this when you work it out. Okay, so there must be some little h prime and some little k prime that I can compose together, which of course will give me some element in capital H productive with capital K, but that when you work this out, this composition here gives you the same as this composition here, and therefore this is going to be the element of this. So indeed, here is the inverse for H composed with K in the product of the subgroup H with the subgroup K. So indeed it is going to have inverses in it. So indeed this now does obey the axioms of a subgroup. So if this is true, if it's true that the product of H with K is equal to the product of K with H, then it's also going to be true that the product of H with K is a subgroup of capital G, and of course that means that also the product of K with H will be that same subgroup of G. Now what we want to prove is only if, and only if amounts to proving the arrow in the opposite direction, i.e. that if it's a subgroup of G, then the product of H with K is going to equal the same as the product of K with H. Okay, so I need to prove this arrow, because if it's true that this arrow is true, i.e. whenever this is true, it implies this is true, then it must be the case that the only way for this to be true is if this is true, because if this wasn't true and this was true, you derive as a contradiction, because this being true implies this is true. Okay, so the only way, if this arrow is correct, if I can prove this arrow, then the only way for this to be true is if this is true, because if this wasn't true, then this couldn't be true, because if it was true, it would imply that this was true, which is a contradiction. Okay, so we need to now prove this arrow. So we need to start with the assumption that the product of H with K is a subgroup of G and prove that it implies that the product of H with K is equal to the product of K with H. Okay, right, so that we'll go over the page and prove only if. So now, only if, and I'll just underline that with orange. Okay, so how then are we going to prove that the product of H with K is equal to the product of K with H? Okay, well, we're going to use the standard trick to prove that two subsets are equal to one another, and that's to prove containment both ways round. So if we can prove that the product of H with K is contained within the product of K with H, and that the product of K with H is contained within the product of H with K, then we're in business. We can conclude that they're equal to one another. So let's indeed do that. So we are starting with the information that the product of H with K is a subgroup of the group capital G. Okay? Now, we know that this product will contain the subgroup capital H. Okay, so capital H will be a subgroup of the product of H with K, and it will also contain capital K. So K will be a subgroup of the product of capital H with capital K. The reason being that you could just, when you're constructing this, let the little k equal the identity element and then run through all the elements of H. Okay, and then you'd get all of the elements of H. So all of the elements of H would end up in there, and the same trick applied in the opposite way to prove that all the elements of K are in there. Okay, so we can conclude that both of the original subgroups are indeed in the product of H and K here. Okay, now if both of these are contained within there, then I claim that I can instantly conclude that the product of K with H is going to be a subset of the product of H with K. Now why can I conclude that? Well, I can conclude that because this is a subgroup, so it's going to be closed under composition. All the elements in here are of the form an element of little k, an element of k rather, composed with an element of H. So little k composed with little h, where little k is an element of capital K, and little h is an element of capital H. All of these products are going to have to be in this subgroup here, because all of the elements of capital H are in it, and all of the elements of capital K are in it, and it must be closed under composition. So all of these answers here, they are going to have to be in there. Okay, so because it's a subgroup, I can conclude that the product of K and H has to be contained within the product of H with K. Okay, now all I need to do is prove containment the other way round. Now that's slightly more difficult. So how am I going to prove containment the other way round? Well, the way I'm going to prove containment the other way round is I'm going to take an arbitrary element of capital H producted with capital K. So here is my arbitrary element, little h composed with little k, which is an arbitrary element of capital H producted with capital K here. And I want to prove that this has to be contained within the product of capital K with capital H. Okay, so that's where I'm trying to aim with this, so that then I can show that all elements of the product of capital H with capital K are contained within the product of capital K with capital H, and then because I've proven containment both ways round, I'm done. Okay, so how am I going to do this? Okay, well, because this is a subgroup of capital G, I know that the inverse of this element must be in there. Now the inverse of that element is little k inverse composed with little h inverse. So this is going to be an element of, whoops, I was about to write k composed with h, but no, it's going to be an element of capital H composed with capital K, or rather, sorry, the product of capital H with capital K. Okay, it has to be because this is a subgroup. Okay, now we know that everything in that product of capital H with capital K is of the form an element of capital H composed with an element of capital K. So of course what I can do is find some, let's say, little h bar and some little k bar from capital H and capital K respectively, which when they compose together will give the same answer as this, i.e. this product is the inverse of this element. So what I can now do is write that little h composed with little k is equal to little h bar composed with little k bar inverse. But now what's the inverse of this going to be? It's going to be little k bar inverse composed with little h bar inverse. Okay, so I now have that little h composed with little k is equal to little k bar inverse composed with little h bar inverse. Little k bar inverse is an element of capital K. Little h bar inverse is an element of capital H because they're both subgroups. Okay, and therefore this is going to be an element of capital K productive with capital H because it's something in capital K composed with something in capital H. So what I have been able to do is write my arbitrary element, little h composed with little k, as something in capital K composed with something in capital H. I've given you a trick to be able to find an element of capital K and an element of capital H, such that when you product them that way round, an element of capital K composed with the element of capital H, you get this element, this arbitrary element of the product of capital H with capital K. So I've now shown that anything here is also going to be in here because this was completely general. Okay, so it'll apply for all elements of the product of capital H with capital K. So now that shows me that capital H productive with capital K is equal to the product of capital K with capital H. Okay, so this truly is true. Now both of these together obviously then implies that the product of K with H is equal to the product of H with K, okay, which is exactly what we wanted to prove. If the product of H and K is a subgroup of G, you can instantly conclude that the product of H and K is equal to the product of K and H. Okay, so it is only if. So now we have proven theorem 2. The product of H and K is going to be a subgroup of G if and only if the product of H and K is equal as a set to the product of K and H. And note that does not require all of these little products in here to be equal to the themselves the other way round. Okay, you do not require all of the products to commute. You just require every product in here to have something in here that gives you the same answer, but it doesn't necessarily just have to be the one the other way round. Okay, and also because we know that if we're working in an abelian group, this will always be true that the product of H and K is the same as the product of K and H, then we can instantly conclude that in an abelian group, the product of H and K is always going to be a subgroup of the group capital G. Okay, so we'll have a break here, and in theorem 3 we'll take this theorem a little bit further.